Alright class, going on to our next section in chapter 10 over inscribed angles and polygons. This one talks about more if you have a point that's not necessarily the center. So instead of talking about central angles, we're going to see what happens when we move a point and we find different measures of angles, because our arc angles are going to be a little bit different. We'll also talk about how polygons play a big role inside circles as well as triangles and in quadrilaterals. We also will kind of hit on vertical angles as well, and so kind of keep those in mind when we talk about angles and what they mean in circles. So we have a few definitions that we need to discuss first, and our first one is an inscribed angle, and this is an angle whose vertex is on a circle and whose sides contain chords of a circle. So that is an inscribed angle. We'll also have an intercepted arc, and that is an arc that lies between two lines, rays, or segments. Okay. So that's an intercepted arc. So then we're going to talk about a subtend, and a subtend is kind of like a chord or an arc. So chord or arc where the endpoints lie on the sides of an inscribed angle. So that is a subtend, and we're going to go visually kind of see what these definitions are towards the bottom. On an inscribed polygon is when all its vertices lie on a circle. So this is kind of where you take a polygon, so any more than two-sided shape that's inside of a circle. Then we have a circumscribed circle, and that is where the circle itself contains the vertices. So sometimes they won't touch the edge. This is where the polygon touches it. This is kind of what the circle is when the polygon's inside. So these are our 5 definitions. And so now we're going to talk about our core concepts. So note you can always pause at any time, but I'm going to go ahead and move this off up. So we have inscribed angle and intercepted arc. So we kind of talked about these. We have an inscribed angle, a vertex that is on a circle and whose sides contain chords of the circle. An arc that lies between is called an intercepted arc. And then if the endpoints of the chord lie on the sides of an inscribed angle, then the chord or the arc is said to subtend the angle. So this is your inscribed angle. So this is kind of where it lies in the end. And then our intercepted arc is here, and then it also subtends to angle B. So it's kind of like if you were kind of like partnering these up together. B kind of subtend, or arc AC subtends angle B, but also its chord does as well. So the intercepted arc, and then you have an inscribed angle as well as your chord AC is a subtend of angle B as well. So that is just a core concept, but we wouldn't use these core concepts without applying them into our theorems. And so our first theorem of the section is 10.10, the measure of an inscribed angle theorem. So the measure of an inscribed angle is 1/2 the measure of its intercepted arc. And so this formula here is going to help you understand that concept. So if we were trying to find angle ADB, so this angle here, then we need to take half of our arc AB. And so I have a couple of examples here that we're going to use. So you have circle P, so that's where you have a circle with the center at P, and QRT is 50 degrees, as well as arc RS is 48 degrees. So this is talking about the arc, and this is the measure of the angle being 50 degrees. And so I want to find the measure of angle T. So I want to find this one. So in order to do that and applying it to this theorem, I know that it is part of RS. And so in order to find angle T, I'm going to take 1/2 of my intercepted arc, which is RS. And so I have 1/2, and we know that arc RS is 48 degrees. And so half of 48 gives me 24 degrees. So angle T is 24 degrees. Okay, and our next one, we're trying to find arc Q. We're trying to find arc QR. This one's a little different. So before I want to find QR, I want to go ahead and find QT. So this is its intercepted arc. So QT is the intercepted arc. Let's go ahead and find that before I get into QR. And then you'll find where the pattern's going. So if I have angle R, or QRT, we'll call it angle R, is equal to 1/2 of the intercepted arc QT. Well, I'm already given R, so I have 50 equal half of QT. So in order to get rid of that half, I'm going to multiply by 2. So now I have 100 equals QT, or arc QT. So this is 100 degrees. So I found QT, but I want QR. So this is that other part. So note that RPT is a diameter. So that means the measure with the diameter included is 180. It's a semicircle. So in order to find the rest of this, I can take 180 of the semicircle, subtract it from 100, and I get 80 degrees. And so I have 80 degrees for arc QR, which is what I want to find. So that's a couple of examples on how to use the measure of an inscribed angle theorem. Alright, so we're going to go ahead and move on to our next page. Again, you are more than welcome to pause in order to write. There will also be snapshots of this uploaded to Canvas, so you are more than welcome to kind of write these if you need to write them separately. But please watch the video so you can get a better grasp on what you're copying down. So our next theorem is the inscribed angles theorem of a circle. Inscribed angles of a circle theorem. And so this is kind of telling you about like matching angles. So if two inscribed angles of a circle intercept the same arc, then the angles are congruent. And so this is saying that these two are the same because they have the same intercepted arc. So that would mean that angle A is congruent to angle B because they have the same intercepted arc. So in this case, for our first example, we want to find angle A. Well, angle A intercepted arc is BD, and C's intercepted arc is BD as well. If angle C is 68 degrees, that means angle A must also be 68 degrees. And so BD is that their angle's intercepted arc is AC, so that means B must be congruent to angle D. Okay, and that is 10.4's one of their theorems on inscribed angles of a circle theorem. Our next theorem is the core concept is the inscribed polygons. This is where you have any number-sided polygon that's inside your circle. So is an inscribed polygon. This is the inscribed polygon. All its vertices lie in the circle. So this is all the vertices of this pentagon are inside the circle. And the circle that contains this vertices is called the circumscribed circle. So that is a core concept that we're applying, and we're going to use it in regards to right triangles and quadrilaterals. So our next two theorems deal with such that. So I have the inscribed right triangle theorem. So if a right triangle is inscribed in a circle, the hypotenuse is a diameter of the circle. Okay, so the hypotenuse is always going to be the diameter. Conversely, if one side of the triangle is the diameter of the circle, then the triangle is a right triangle, and the angle opposite is a right angle. So, note the hypotenuse here on this given example and here is a diameter, and so that means that if we were to make two chords from one part to the next, we create a right triangle. So in this case, I have a right triangle inscribed into a right triangle that is in this circumscribed circle, and I want to find out what x is. Well, I know that this wy is my diameter, and that would make wxy 90 degrees. However, we have 5x here, and that's what we're trying to solve for. So I will have 5x equal to 90, and when I divide by 5, I get x equals 18 degrees. X equals 18. All right. So now we're going to do the same thing with 10.13 Inscribed Quadrilateral's theorem. This one's a little different because we talked about how same sides should add up to 180. This one's different. The opposite sides are going to add to 180. So a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So the key word here is opposite angles are supplementary. And remember, supplementary means they add up to 180. So opposite angles are not going to add up to 180. Not like the other ones where same side we're going to add to 180. So this one I said is a little different. So in this example, we want to find z and we want to find y. Well, we're going to go off our formula. We know that opposite angles have to be supplementary. So supplementary to, or what would we add to d in order to get 180? Well, it would be f. So we know that we have to have d plus f to give me 180. So we already know that d is z degrees and f is 80 degrees. So to solve for z, I'm going to subtract 80 from both sides. So z equals 100. And then I will do the same thing with y. Well, I know if I add g and e, I should get 180 degrees. We know that g is y and e is 120. So I'm going to subtract both sides. So y equals 60 degrees. Alright, and so that is how you use it for quadrilateral theorem. So keywords here are opposite angles are supplementary. That is going to be very important in order to find those missing angles in your inscribed polygon. So let's go on to our next page. Extra practices side. So on our extra practices side, we are going to find, using the diagram, find the indicated measures. So in this sort of examples, we're talking about angle A in question 1. So angle A is here, but what do I already know? I know that CB is a diameter. So if CB is diameter, that means I can create a right triangle. And fortunately for us, that A turns out to be 90 degrees, and this is because of the inscribed right triangles theorem. Okay, so that could be a reason why that this will work. So number 2, we're looking for the measure of angle C. Well, I already have 28 degrees, and I know that angle A is 90 degrees because it's a right triangle. And so we know that all triangles add up to 180 degrees. And so in order to find a missing angle, I would add 90 plus 28, and I would get 118. And I need to subtract this number from 180. And so my final answer is 62 degrees for angle C. Okay, so that's for the inscribed right triangle theorem. So now we're going to find some measurements. We need to find BC. So and BC is in fact our diameter, and I have a chord. I have 2 chords already given, and so I can use the Pythagorean theorem. So I'm going to put it over here. So I have 3.9 and I have 7.3, and so these are my legs, and C is my hypotenuse or my diameter, however you see fit. So I know I'm going to add 3.9 squared plus 7.3 squared, and I would get all that to C squared. And note that you have to square root both sides. So I can take the square root of 3.9 squared plus 7.3 squared to give me C. And if I'm going to put all of that into my calculator, I end up with a rounded decimal of 8.3. Awesome, awesome. So now we're going to find arc length. So I have an arc length. I need to find the arc length of AC. So this is what I need to find. AC, that arc length. And so what is the intercepted, or what's the inscribed angle? So the inscribed angle is actually 28 degrees. So 28 goes with this. This is where we use the formula for finding half. So in order to find angle B, we know we would take half of AC, of arc AC. That's how we would find an angle. So all we have to do is plug in what we're given. Angle B is 28, and we're trying to find arc AC. In order to get rid of a half, I multiply it by its reciprocal, or in this case 2. Reciprocal of 1/2 is 2, so I'll multiply both sides for a 2. So I have 2 times 28, that gives me arc AC, and 2 times 28 is 56. So arc AC is 56 degrees. Alrighty then. So that is 1 through 4. Let's move on to number 5. Number 5 says we want to find arc AB this time. So we have arc AB. Now this is where I said remember that CB is the diameter. So don't forget that. So if we need to find out, we have CB is the diameter, and when we have the diameter, the entire half of this circle is 180 degrees. So that measure makes it a semicircle. So it's 180 degrees. So we've already found that AC was 56. So now all I have to do is subtract 180 from 56 to get my remaining angle measures. So I have 124 degrees for AB. Alright, so that is 1 through 5. So let's move on to number 6 and number 7. So number 6, it says to name two pairs of congruent angles. So let's talk about, we have angle ABD. So we have this angle here, and then we have angle BAC. So we have B and then AC. So these are two different angles. So note these cannot be the same because they're kind of like think about putting them in the same triangle. The two can't be really the same in this particular notes with circles. So these two have to be different measurements. So what's the one that shares the same intercepted angle? So this one shares an intercepted arc, and that would be C. So what's congruent to ABD would be ACD. And then we have what would be the same with A, it would be D, because they share the same intercepted arc. And so what's congruent to BAC would be angle BDC. Alright, so those are your congruent angles that you would label. And then in our last one, we have the Inscribed Quadrilateral theorem that you must apply to find a variable value of each number, value of each variable. And so we know we need to find M, and we know we need to find N. And so if we want to find M, we know that the opposite angles are supplementary. So op angles are supplementary. So we know they must add up to 180 degrees. So in this case, what is opposite of angle A is angle C. So I know if I have M plus 65, it should give me 180. So subtract 65 from both sides. And so M equals 115 degrees. And then I will do the same thing for N. Well, what's opposite of N would be D, or opposite of B is D. So if I add N plus 100, I should get 180 degrees. And I'm going to subtract 100 from both sides. And so N equals 80. And that is our last example for our extra practices. Thank you so much for watching my video. I hope this helps. Again, you can find snapshots of this later on. I also have tutoring Wednesdays and Thursdays after school till 4 o'clock. Thank you so much.